Hello, this is Jonathan Templin, and this is an online lecture about multivariate models, model setups, and assumptions. Really an introduction to multivariate models. In this lecture, what we're going to see is an introduction to linear models and how to estimate them using the Lavaan package in R. Lavaan is a path analysis and structural equation modeling package, but we're going to use it for our purposes in multivariate models as well. We're going to focus on what the parameters mean and how they relate to a multivariate normal distribution. But before we do all that, I'd like to start with some overarching information about just multivariate models in general. This is the first installment of a series of lectures trying to give an overview of the idea of multivariate modeling, in particular using multivariate linear models. Multivariate models are distinguished by having more than one outcome or dependent variable in the analysis. And so this differentiates them from our univariate models where we predicted one outcome only. Our focus for these models will be on situations where our dependent variables, or our outcomes, are plausibly continuous. I say plausibly because we're going to use an error term that is a multivariate normal variable, or set of errors that are multivariate normally distributed. And when we do that, because of the normal distribution having a range or a sample space or support that is the real number line, negative infinity to positive infinity, what we're really assuming is that our observations follow a conditional normal distribution, and so therefore they must be continuous as well. But what you're going to find out is that this assumption or this use is really just our first case because the normal distribution simplifies a number of things. And so really there are generalized versions of multivariate models that are possible. Those are much more complicated, and we'll probably stay away from them for this class. But in concepts, you can do any type of distribution involved in a multivariate model itself. Now, there are classical approaches to multivariate linear models. When I mean by classical, I'm talking about statistics that date back into the 1920s and 1930s, if not before then. And if you take a traditional or classical multivariate textbook, what you'll find is a bunch of chapters that talk about things like multivariate analysis of variance, or MANOVA, and multivariate regression. So why I'm moving away from those methods, because quickly you'll find that those methods have some restrictive assumptions that don't lend themselves well for data that you might have. For instance, the methods of MANOVA and multivariate regression often get estimated with least squares. Least squares itself has some problems in that it has a really restrictive set of assumptions when you have missing data. It assumes the data are missing completely at random, and that often does not get held in typical data sets. Whereas when we use a different type of estimation method, particularly maximum likelihood or Bayes-based versions of estimation, you'll find that assumption of missing data being completely at random is relaxed a little bit. So it's a little bit better for them. What that means is if you have a set of outcomes you're trying to measure, maybe you have a repeated measures design, and you're trying to get 4 pieces of information from a person, maybe 4 time points across a semester or something along those lines. If a person does not provide information for one of those time points in your least squares analysis, multivariate ANOVA or multivariate regression analysis, we're going to end up finding that we have to throw out all the data for a person. Whereas in the methods that we're going to use today, we can use whatever data a person gives us, and if they're missing one or more of the outcomes, that's fine. We sort of resize the model to make it work for them. Furthermore, the classical methods of MANOVA and multivariate regression often provide very, very limited methods of setting what is going to become important for us is covariance matrix structures. What I'm talking about with this is that when we have a multivariate set of observations, we have a covariance matrix that goes with it, particularly in the multivariate normal case. And for that, what we're going to find is it's very hard to estimate the full covariance matrix. It's just something that MANOVA and multivariate regression try to do. So people have come up with a number of ways of trying to simplify this problem. And and really the only option for that in a classical approach is a very oversimplification of the issue. So it allows us, these modern versions of multivariate methods really allow us a little bit more flexibility with respect to the covariance matrix. Furthermore, if you go and try to estimate these models, they basically take every predictor variable that you might have and map them onto every outcome, where that often is not really the case. It doesn't necessarily have to be the case, and so our new methods don't do that. These old methods don't really give you much information about how well the model fits the data in an absolute sense, particularly when you have the reduced covariance structure. And it also does not really provide an easy way to do model comparison, nested and non-nested models. So really what I'm talking about with most of these points is the use of some type of likelihood-based, typically ML version of estimation enables most of these to be possible. And what we're going to find is that our ML methods that we're going to do today really are versions of MANOVA and multivariate regression, but those things are subsumed, or said to be subsumed into this modern approach I'm going to tell you, which means they're included or absorbed into something else. This is the definition on dictionary.com that I found. So what that means is that what I'm going to teach you today will allow you to do what the classical methods do, but will also do much more. It's a much more flexible approach. So at the very minimum, you'll be doing MANOVA multivariate regression, but most likely you'll end up in cases that wouldn't quite fit into one or the other, which is nice because most of the time data that you have don't fit into these approaches. The other thing I'll note is that you may have an advisor or someone you're working with who insists that you really do a MANOVA for a type of analysis or some type of multivariate regression. Because the methods are subsumed, or said to be subsumed, into this modern approach, you can show that you're actually doing MANOVA or doing multivariate regression when you're using this approach. Even though it doesn't look like MANOVA or it doesn't act like the MANOVA that the person that might have learned it previously understands, it certainly is it. And later in a later lecture, I'll show you how the two correspond. So there are really three approaches to doing estimation of these multivariate linear models. And really they're sort of driven through software. The actual underlying theory underneath each of these is the same. So really we might be using some type of path analysis software. This is typically what we're going to start with here. This is Lavaan. Or we might do this through linear mixed model software, which we'll get to next, which is the LME4 package in R. Or we might do this in a Bayesian network approach, which often gets implemented with a Bayesian package, and I'd like to show you that at the end, one of the later lectures in the semester. But really, the theory behind each of these approaches is identical. I mean, absolutely identical themselves. There's a general overarching theory of everything that that fits into. But the main difference between all three approaches is software. Right? So some software does a lot. And what I found up to the date of this recording, March 2018, is that M+ is likely the most complete of what you find out there, although some of the Bayesian packages are so general you can pretty much do anything in those as well. So it's really hard, though, to find one package that does it all, and so my approach for teaching you this in this class is to try to teach you a little bit of each approach just in case you find yourself in a situation where you might need them. Now, why you might need them, I'll wait till a later class once we actually describe what they are, so you don't have too much to keep track of, although there's already enough to keep track of in this class as we begin with. So today we're going to start with path analysis. The reason I'm using path analysis to start with is because it's a very direct modeling method in that you can actually specify the outcome versions that you see, the outcome variables that you see in the analysis, and provide the direct linear model for each outcome, just as you would in a typical, if you were doing univariate analyses for each. That's not as direct when we get to the mixed model software, but the problem with the mixed models package, LME4, is that, actually, pardon me, why we need to include that is several reasons. One is the way we estimate variances. Another is if you want the ability to add certain types of random effects into your analysis that aren't easily attainable in Lavaan. And so finally, at the very end, we will talk about Bayesian networks. A later lecture, not very end, but later lecture in the course, we'll talk about Bayesian networks and how they're used in entirely different software altogether, Bayesian software. So the planned course outline is that we're going to go start with Lavaan, with path analysis, because it helps. I think the syntax for it's a little bit more understandable. We're going to move to linear mixed models and go to Bayes. The problem is that each method that you see here, each type of analysis, a 1, 2, 3 here, relies on a different estimation method, which means sometimes the results lack comparability, and that symbol right there is an interrobang. It's a combination of exclamation point and question mark. And you're like, really? That's really what that means. So that means even though the theory behind each of these is the same, you may get different numbers in each due to the way you're trying to estimate things, and that is a big issue. But that's something that we'll just have to live with at the moment. It's not easy to describe why that is the case in our course. But overall, there's a topic in multidimensional modeling that gets shared pretty much across models and across paradigms, and that's something called the Curse of Dimensionality, which I think it sounds pretty funny. It almost sounds like an Indiana Jones movie, in that having lots of parameters in a model creates a number of problems. So what do I mean by that? Well, when we put multivariate data together, when we have multivariate outcomes, we all of a sudden have a lot more parameters to estimate because the covariance matrix of our outcomes is now part of the model. So because of that, as we'll see in just a couple of slides, you quickly start accumulating a lot of parameters that you may have to estimate in such a model, and this causes issues, particularly if you have small sample sizes. It may affect your power. You may need larger sample sizes to detect effects, and you may end up having issues in model fit. Model fit becomes much more relevant as we go forward. You'll see that on the next slide. For multivariate normal data, the reason why there's lots more parameters is that as the number of outcomes increases, 1, 2, 3, 4, we call that linearly, there is a quadratic increase in the number of parameters, meaning essentially it's curvilinear. So the number of parameters that you may have to estimate escalates much more quickly for every variable that you add to an analysis, and that's where we call this the curse of dimensionality. So to be used as an analysis model, why this becomes important is we have to have, particularly in the multivariate normal data, we have this covariance matrix for our data. We have to make sure that our model is effectively recovering this covariance matrix. And that's where we get the foundation of model fit on. Our model must produce data that resemble the data that we have currently. And if it doesn't, then there's an issue, a big issue actually. The model doesn't reflect reality, and therefore our interpretations and inferences from the model may be biased. So in this regard, what we'll find is that the covariance matrix that we imply that we put into an analysis must fit as well as the covariance matrix in the data. And what I mean by that is something called a saturated or unstructured covariance matrix. A covariance matrix that has every possible covariance between variables estimated, along with each variance estimated as well. So on model fit, that is the biggest difference between multivariate models and univariate models. So in univariate linear models, you remember the model for the variance. That was really given by, so if we had y equals beta 0 plus beta 1 x plus e, and we said that e followed this normal distribution of the mean of 0 and the variance is sigma squared e. This term right here we often called the model for the variance. Well, it turns out with one outcome, there's only one variance. This is what we call a saturated model. There's only one value it can take, and we have a parameter. We have one parameter for one variance. It's going to fit identically. In fact, so what we end up seeing is that it wasn't much of a model, but really we put the one parameter there that we needed to put there, our residual variance, and so when we do that, we always got perfect model fit. We saturated the analysis, the number of parameters. But when we get to multivariate models, and the example I'm going to show you, we're just going to start with two variables. From one variable to two, we're going to see that we now all of a sudden have covariances that we have to estimate. And if we don't estimate them, if we don't estimate the covariances, or if we put some type of structure in our covariance matrix, such that we don't estimate every single one of them, we have to make sure that the values we do estimate fit as well as the saturated model, the one where we could have estimated everything. So model fit becomes a very big issue. And so really what we're going to see in the analysis as we proceed, the steps of the analysis are no longer estimate model, look at the beta coefficients and interpret the results. There's an additional step that gets added to the analysis, which is estimate model, and then the next step is check model fit. Once you check the model fit, you have to see that the model fits the data. All right? There are different types of standards for this. We're going to get to model fit in the next lecture, so we will hold on for what that means for right now. But really, we estimate the model, we check the model fit, and then if the model fit is good, then we can go and look at the parameters and start interpreting them. But if the model fit isn't good, it's going to be difficult to believe the results because the parameters themselves will be sort of stretched in ways that don't necessarily reflect reality. So for today, I'm going to talk about an example where we have a very large data set. This data set will continue with this series of lectures up and through path analysis. The data come from data are simulated. So I took this article right here from Pajares and Miller, the role of self-efficacy and self-concept beliefs in mathematical problem solving. This was from 1994, so it's got a few years on it. But I simulated data based on the covariance matrix that they reported in their article. There were a total of 350 undergraduates in their study. Really, it was looking at whether or not how you believe in yourself and what you think of yourself, how that impacts how well you solve math problems. And this is in college students. So we had 350 undergraduates. Predominantly women, 229 women, 121 men, and I randomly knocked out 10% of the values for missing, which was sort of what they had mentioned in their article. Now I want to note if you take a look at this article, if you go find it, you may see the results might differ in what we're doing from where they had reported results, and that's because the simulated data are using a multivariate normal distribution, but really there is some variables that have bounds to them. And so where we have this free range variables that can be any number, they are really actually bounded in practice. So they may not exactly match. The results may not exactly match. But here are the variables in the data set. We have a sex variable where I coded 1 for a person who was a female, a 0 for a male. We have a self-report of math self-efficacy. We have a self-report of perceived usefulness of mathematics, a self-report on a scale for math anxiety, a self-report on a math self-concept scale, a self-report of number of years of high school where a student took math courses. You can tell this study was from the 90s. I think pretty much everybody these days takes 4 years of math in high school. And then prior experience at the college level. So that's another self-reported variable. And then students were given an 18-item multiple choice instrument that we talked about mathematics performance. And you'll note that each one of the variables that I'm highlighting here, and right here, all of these have some type of reported reliability. Now, that immediately will violate one assumption of this analysis in that if we use any of these as predictors or outcomes, our model is assuming these reliabilities are perfect or at 1. And when we put a variable in that doesn't have perfect reliability, we are also likely to bias some of our results. We might see our beta coefficients be shrunken by it, something we call it kind of an attenuation issue, But we also will find that our standard errors of these coefficients will be at much smaller errors as well, and that's because we are pretending to have much more information about a person than we actually do. That's what the reliability is sort of indexing. Now, a remedy for that would be to do some type of structural equation model, and there is certainly a class for that you can take. In educational psychology here at Kansas, we offer that as EPSY 906. But we won't get into that in this course. So just know that to begin with. So we're going to use maximum likelihood. We're going to estimate this multivariate linear model using multivariate normal distribution in our likelihood function, and with the package name Lavaan, which stands for latent variable analysis. Latent variable analysis. Now, what a latent variable is something like a factor from a factor analysis, or a random intercept or slope from a multi-level analysis. But we actually can use it where we don't have latent variables, so it's not really like Lavaan. For us, it would be like observed variables, and I don't even know what the acronym for that would be, so I'm not even going to try. All right, so what we're going to do is use that multivariate normal distribution in Lavaan, and we're going to use maximum likelihood to estimate it. The method of maximum likelihood found in Lavaan is something sometimes called full information maximum likelihood, or the for whatever reason, this annoys me when people say it, but they call it FIML, full information maximum likelihood. Why I make that distinction is because early path analysis software such as Lizroll did not necessarily use full information software methods. And full information is really kind of the gold standard these days. What is meant by full information is that each observation, each value from that dependent variable gets plugged into the likelihood function at some point. Now, since I've been trying to teach you maximum likelihood, you saw that in our ML section where we were able to plug in values to the likelihood and compute likelihoods and so forth. So that seems like, well, yeah, of course, every value has to be there. But it turns out there are limited information versions of estimation, and typically, instead of using all the observations, what we use is a summary statistic. So, for instance, Lizroll would take a mean vector and covariance matrix, or just the covariance matrix in some cases, and use that only for the analysis. And the problem with this is that how you create your summary statistics may be subject to having missing data issues. And so those may be more problematic with summary statistics than with this full information method. So we typically prefer full information over the limited information method these days, and that's one of the reasons why. So you can use Lavaan to do analyses for all sorts of linear models, including MANOVA, repeated measures ANOVA, factor analysis. You could even use it for multi-level models if you wanted to. There's lots of ways that you can trick Lavaan into doing what you want it to do. And we can go back to, if we begin, let me just show you how to use Lavaan, starting with our univariate linear regression. So we're going to start our discussion by the simplest model that we're going to find, which is a univariate empty model, and we're going to take the performance variable. This is the 18-item multiple choice test students took in this study. And we're just going to provide this empty model for it, where we estimate, we say performance is equal to some intercept plus some error term. And the error term has a residual variance, in this case, error variance, sigma squared error. So we're estimating these two parameters, beta 0 and sigma squared error. So here, what you'll notice is there's already a quick difference in my notation in that there are additional subscripts involved in each of these, where I now have beta 0 perf and sigma squared error, comma perf. And that is because when we get to multiple variables, we're going to have an intercept per variable, we're going to have a residual variance per variable, and we need something in notation to tell these apart so that we know that these values pertain to the performance variable, whereas other values of intercept and error variance might pertain to some other variable that we have in an analysis. But right now we're going to start with the univariate method itself. So let me flip over to the R section here. You can download this file from the website. I have it available here. We're going to end up putting in a number of packages to do the analysis today. So we run this needed packages syntax, which will either download them if you haven't downloaded them before, and then load them. I will note that one of these packages, semplot, will take some time, so do be patient when you do that. The examples that we have here are stored, our data set is stored in this data math variable in our EPSY 905 R package. And because of that, I can just load it, and I'm now going to put that into a data frame that's relabeled right here. And so here you can see each of the variables. We're using this performance variable right here for our analysis. Now, we get into the syntax for Lavaan. So let me go back to the slides and talk a little bit through that. The Lavaan package works by taking the typical R model syntax, such as we saw in the LM function, but we take that and put it into a very long quoted character variable. And furthermore, you'll find there's other parts of the syntax involved as well. So let's go back over here to our R syntax. Let me zoom in here. So this is the Model 1 univariate model for performance. This whole section right here, you see Model 01 syntax. That's a variable I'm going to create, and you see there's a quotation mark at the end of this line. Everything from that first quotation mark to that last one is a character string. So if I run this, Model 01 syntax does not run the analysis. What it provides is this character variable here. If I were to repeat it to you, what you see with the /n in front of you is this is the command in regular expressions that provides the carriage return. Basically, when you hit return, it's basically saying there's returns hit between each of these. If I were to do a write.table of Model 01 syntax, you'd see that part go away. So here you see just this long quoted string like we have up here. But you'll note that the values actually themselves turn green inside the quote. It almost looks like a different shade of, it's slightly different shade of green than the comments, which is a little bit frustrating in RStudio, but you can actually change that in the settings if you'd like to. But Model 01 syntax here, going into the quote, let me walk you through what each of these values represent. Just like an R syntax, any line that starts with a pound symbol or hashtag is it's not a Twitter handle or Instagram handle for looking for pictures of variance. No, that is a comment. All right, so I try to comment my syntax early on so you know what's going on in it. The second part now is sort of where we get into Lavaan syntax. There's two parts to this here. There's a part for the model for the means and a part for the model for the variances. I'm going to start with the model for the means first. The model for the means, this perf tilde1 is exactly what we would have found if we did the LM function. And to show you, let me just, if we were to run this empty model with LM, if I do LM and I type formula perf tilde1 and the data is math data, that will run the analysis just fine. So this is the part of this model for the means is the part of the syntax that you are familiar with already. The model for the variance is a little bit more now plays a role because now, as I mentioned before, we have this big covariance matrix potentially. Although in this univariate model we don't. But we may, in multivariate models, have a very big covariance matrix. So this allows us access to each of the parameters of that covariance matrix. And the way we interpret this syntax is the following. Any variable on the left-hand side, whenever you see the double tilde, that means this thing on the left-hand side, what we're talking about is the covariance of the thing on the left-hand side with the thing on the right. Now, again, a covariance, we only have one variable in our analysis. What's a covariance here? Well, the covariance of a variable with itself is its variance. So when I say this line right here, what I'm talking about is this is going to provide an access or tell Lavaan specifically to estimate the variance of this performance variable. I will note also that this part of the syntax is actually unnecessary, but I'm providing it here just to show you how to access the variances. By default, once you put a model in for the means, Lavaan will try to estimate its variance. Okay, so that is our syntax for Lavaan. Again, that does not run the analysis. The next thing we do once we code up that syntax is we plug it into this SEM function. And that SEM function does the work for us. So let me go back to that function itself. Here, the SEM function, it takes the syntax as its first argument, data as its second, and the next three options that you see here, I'm going to ask that you leave constant for the rest of what we're doing in class. Mimic equals M plus is important because it helps us provide, a lot of people use M plus. I don't like it particularly, although it is very good at what it does. I don't like that it costs so much money and that students would have to pay something like $300 or $400 or $500 to use it. So I stick away from it, but because a number of people use it, we're going to have it as our mimic here, so our results will actually tend to look like M plus. Fixed x equals true treats if we had any predictors, it treats it as those as fixed values, although we don't, why that matters is less important today. You'll find out a little bit more about that when we get to path analysis. And then finally, the estimator equals MLR is the type of estimator we're using. It actually stands for maximum likelihood robust, or robust maximum likelihood. And I'll discuss that in another lecture as we go forward. But once we put all this together, once again, syntax is the first argument, data is second, and the last three arguments are just sort of default for us, so keep those there. We now run this line of code. It takes a second. It tells us a warning message. This is telling us all these cases that are empty. What this means is every observation, these are the rows of the data of observations that have missing data on our dependent variable. What you'll find is in Lavaan, what it will do is try to take the missing data, and if you have multiple dependent variables, the only time it gives you this warning is if a person has missing data on all of them. If a person has data on one or more of them, they won't be included in this warning. For us, we only have one variable right now, which is performance. So this is just going to tell us all the missing data for performance. So now, just like when we ran the LM function, this model01 fit is the object that contains all of the information for our analysis, and we plug it into the summary function. But now we're going to add this default ending to it, this default argument where we say fit measures equals true. The Lavaan version of summary actually has more information that it shows than what comes out of what we get from LM. And that's because there's just a lot more information coming from this type of analysis when we do things. So let me show you the summary here. It pops up a bunch of numbers. Everything at the top we're going to ignore for today, but we will come back to that in the next lecture or the next several lectures. The main thing that we're going to talk about are the parameter estimates values that are down here at the bottom of the analysis itself. And if I flip over the slides again, I can just zoom in on that one section, or at least hope to zoom in on it. My slides are now paused. Let me see if I can fix this. Well, technology breaks in the middle, but that's okay. I have a backup. I actually have the slides on here as well. Let's pull those up. Oh, there they go. It finally worked. Here we are. This is the zooming in. Remember, this is the zooming in of us on that model parameter estimates output. So once again, we're going to zoom in on this section of output right here. We're going to start talking about what each of these parameter values mean on the slides. So here on our slides, we can see there are two parameter estimates, one for the intercept and one for the residual variance. There's the intercept. There's the variance. Intercept of 13.966, variance of 8.751. And you'll note this is on the scale of variance. This is not a standard deviation like we would find in LM. So what this is telling us is that we assume when we have no other predictors in our model, this is effectively giving us the mean. This is telling us the mean of our data. The mean of performance is 13.966, and the variance of performance was 8.751. So that's telling us really, once we assume this normal distribution, that we think that performance follows a normal distribution with a mean of 13.966, variance of 8.751. And to get you thinking about model fit, let's just take a look at how well this model fits the data. This is a plot of our variable, a histogram, and then this dashed line that you see here is our kind of an empirical histogram, a smooth line over the histogram itself, whereas this dark solid line happens to be the actual the normal distribution would say. And you'll see that these things lay right on top of each other, and that's because in the univariate model we have literally perfect model fit. The only reason why we see these little deviations here might be rounding error or other fluctuations that deal with numbers in the computer more than the actual concept themselves. The other thing I'll note is the sample size. Overall, we had 350 people in our sample. This analysis used 290 of them. Why I'm talking about this is because when we start to get into model comparison, we have to compare two models that may or may not be nested. We have to compare them. They have to have the same people, which means we start with the same sample size. So it's good to note how many observations are in each. Okay, now we're finally ready to take the next big, bold step. We're going to go to our very first multivariate model, and we're going to keep it empty. The empty model is nice because it's supposed to look like the data. So we're going to add one more variable. Right now, we have two variables to look at. We're going to look at mathematics performance again, and we're going to look at perceived usefulness, which is actually given by the use variable name. Excuse me. We will assume these two to be continuous variables, and we're going to use this conditional multivariate normal, although we don't have any predictors, so there's nothing to condition on. This is just literally going to be multivariate normal to estimate this. So this empty model we're going to build is a baseline model, as you know. It's going to help us talk about how the models look based on the characteristics of the multivariate normal distributions. We're going to be able to take each of the parameters that come out, plug that into multivariate normal, and we're also going to be able to compare that with our observed data to see how well this covariance matrix matches the data that we have. So here's the model itself. Now, instead of having one regression, like you saw this here, we're actually going to have two. And that's what happens in a multivariate regression. We literally are drawing out equations for each of the regressions that we have, each of the dependent variables. So here we have performance as a dependent variable, usefulness, perceived usefulness as a dependent variable. For the performance equation, we see that there's an intercept and a error term, and for the perceived usefulness equation, we see there's an intercept and an error. And again, you see the subscripts for each of these denote which equation or which dependent variable they are attached to. Now, previously we had seen in a univariate regression that this error term would follow a normal distribution with some sigma squared error for performance. And sure enough, PERF, yeah, that's right. Right there it is. So when we have two variables, we often start by thinking that both of these now follow a multivariate normal distribution for error. And similar to the univariate normal, each variable's mean we're going to assume to be 0. Each variable's variance we're going to assume before is the same, sigma squared error for performance, sigma squared error for usefulness. But now, this side of this notation right here is the mean vector. This other side right here is the covariance matrix, which sometimes gets the label R, but we're going to leave that off for right now. I'm not going to focus on that right now. So again, here's the two error terms. Each of their means are 0. Down the diagonal of the covariance matrix, we can find their covariances, or their variances. So this is the error variance for performance. This is the error variance for usefulness. And the off diagonal then contains, remember this is a symmetric and square matrix. This contains the covariance. All right, so this value here is actually going to be equal to this value here. So there's actually one parameter additional. So this covariance talks about how related our error terms happen to be. And in this analysis, because it's an empty model, this is actually going to be an estimate of our sample covariance in our data. So we're going to see how close we are to fitting our data with this. So you'll note when we go from one variable, in a one variable regression we had two parameters. All right, so if we did just this linear model for performance or linear model for usefulness, we would have 2 parameters each. But when we put them into a model simultaneously, we now have not 4 parameters, but we have this additional term, this covariance right here, which actually makes it 5 parameters that we have altogether. So because of that, we have one additional term to estimate. Now, if we go and start doing some matrices, I know you don't want to see this, but maybe just give it a shot. Really what's going to happen with this multivariate model is that this matrix form right here has all of the variables plugged into it already. And what we can see is if we plug in, we have a column vector for our betas and a column vector for our errors, we could have a design matrix X that sort of dictates which beta goes where, and we can get this same thing together. Well, let's not dwell on that for right now. Let's go and run this analysis, or actually let me go talk about the syntax real quick. Back to R, back to my source. So now, go down to Model 2. This syntax has a little bit more stuff in it. Again, we see for the model for the means, we have performance ~1, so we're going to get an intercept for performance. Use ~1, so that's our intercept for usefulness. In the model for the variances, we see performance ~performance, that's the variance of performance. Usefulness ~useful, use, which is our variance of usefulness. And our covariance section will now give us performance ~usefulness. So this is the covariance parameter. So each one of these 5 lines of syntax happen to represent each of the 5 parameters in our analysis themselves. And so if I go back to the slides, you'll be able to tag each of those together. This is the mean for usefulness. This is the mean for performance. This is the covariance between the two. The variance for performance and the variance for usefulness. So we're actually estimating all the terms of this covariance matrix. There's 3 unique parameters. So what we're going to call this is the saturated covariance matrix. A saturated covariance matrix is one where we've estimated all parameters. Similarly, if you are in a different camp, a different line of work, saturated is often a term we use in structural equation modeling or path analysis. In mixed models, this is often called an unstructured covariance matrix. So we're literally estimating everything, not putting any structure on it whatsoever. What's notable about the saturated or unstructured covariance matrix is that no other covariance matrix can fit better. None of them can. This is the best model fit you'll get in this class of model. So the only thing you can hope to have with a different type of structure is a model fit that is as good as this model. So if we run our analysis, go back to R, we run the syntax section, we plug it into the SEM function with syntax first, data second, and then that stock last 3 terms. It takes a little bit longer to run now. Only gives us 1 warning now instead of so only 2 observations were missing on both performance and usefulness, whereas before we had some 60 observations missing all of performance. It's a little bit different. Now when we go to our summary for this, we're going to dwell on the bottom part, the parameter estimates themselves. Flip back to the slides, not those, these, and you're going to see these heads up. So what we're going to find here is this is the mean. This is beta 0 for performance. All right, so that's our estimated performance. You'll see this mean is actually identical to what we estimated prior to this. This is our variance of performance, and this is also identical to what we've estimated prior to this. If we go back to our univariate model, if I can pull that up real quick, the mean was here was pardon me, I've got these backwards. Excuse me. Erase this. Okay, starting over. Intercept beta 0 is right here. Beta 0 for performance 13.959. Variance of performance 8.742. This is sigma squared right here. If I go back to slide 17, I can see that we saw 13.966, 8.751. You'll see that within rounding error, those are about the same. And the reason why they're a little bit different is because now we have we have more observations in the analysis, so it's doing things differently with that missing data. Now, what this is telling us is the mean of perceived usefulness is 52.440 with a variance of 249.245. And this last term right here is the covariance, 6.847. So that is our covariance between both usefulness and performance. And if I wanted to be bold here, I'm going to try something different in R. What is a covariance? Well, a covariance is very difficult to actually estimate. Actually, I'm not really being bold. It's right here. The covariance is difficult to interpret. So instead, I'm going to switch this over to a correlation. And this is going to tell us that our correlation between performance and usefulness is 0.146. So if I were to go look in our data, see how this related to the data itself. X is math, data, star use, and Y is math, data, star performance. Oops, it doesn't like that because I didn't take care of the missing observations. So in this case, I'm going to do use. We're going to say pair wise complete observations. And now we'll see the correlation in our data was 0.149, whereas in our estimate was 0.146. They're very close. Part of that is our missing data. The way that we estimated this handles missing data differently than the way that the correlation here does, the pairwise complete observations. By handle, I mean we estimate this using maximum likelihood, which has a different assumption of how the missing data are actually found. So let's go back to our slides now. One thing we can do is plot this model. I want you to understand the multivariate normal distribution. What this model is telling us is our data should start to fall. This is the density or the multivariate normal. If this is usefulness and performance, if you take any pair of values for a given person, this tells you how the height of this surface tells you how relatively likely they are. I then took that surface and superimposed it over our data using, or flew over the top of it really, using these contours themselves. And what we should find is most of our data are within those contours. That's sort of the region of where the data should be concentrated. There are a lot of data that are out here outside the contours, but that may or may not be. That seems to be relatively understandable in this case. What you don't see is that the dots that are stacked up right on top of each other. There's much more that are in the circles themselves. So now here's the thing about the problem or the curse of multidimensionality. After looking at our first model here, is that as more dependent variables get added to a multivariate model, more outcomes, you'll note that the number of parameters gets very, very large. And here, this is what I'm talking about. Here, this black line is the number of outcomes. This red line, or this green line, are the total number of parameters in the model itself, right here. And so as this goes up linearly, as you see this line, as the number of outcomes go up, the total number of parameters, particularly this is an empty model right here, just jumps up curvilinear. It's essentially a quadratic function. The reason why is this red line. That's the number of covariance matrix parameters. Right? So every time you add a variable, you add a mean for it, or a beta 0. You add a variance for it, which is a sigma squared, but you also add a covariance with that variable and all the other variables in the analysis itself. And that covariance thing is really the part that really takes up the space. Okay, let's go with another model though. Let's start playing around a little bit. Here, we're going to demonstrate how models, this is a model that we're going to carry with us into our next lecture, which is about model fit. But this is to demonstrate how models vary and sort of their implications for data, particularly with respect to model fit. We're going to estimate a model where we set the variance between performance and usefulness to 0. Right? So when we do this, we're implying 0 correlation between these variables. We saw our model estimated correlation was 0.14. That wasn't too far from 0. Let's see how this works comparatively. Now normally you wouldn't necessarily do this in a real data analysis, and if anything you'd start with a zero covariance matrix first and then plug in covariances as you go along. But I'm doing it now to show you how models work in a multivariate sense, and really to set up how on earth are we going to compare, why and how are we going to compare these models together. So the syntax for that, go back to R here, scroll on through this. All this other syntax I'm skipping here is for plotting. You're welcome to see that and use it on your own if you'd like. Here's Model 3's syntax. This is very similar to Model 2's syntax. The only difference is under the covariance section, to not estimate that covariance, to set it equal to a value, I put the value and a star in front of the variable on the right-hand side. So this is telling Lavaan, take the covariance between performance and usefulness and set it equal to 0. So our model now will only have 4 parameters in instead of 5. So now we run this, we get our typical warning of the 2 cases that had missing data. We saw that before. And we can go look at our results. What this is doing, though, is we're assuming this is 0 value now in our multivariate normal covariance matrix. And here are our results. For the covariance, you'll see this section has a 0, and the key to understanding this was set is that there's nothing in the standard error section, nothing in the z-value and nothing in probability. The way they put Lavaan is a little bit nicer than M+ in this regard. When you set a 0 value in M+, the standard error becomes 999, which is really, could be a number, but let's just leave that at that. It's blank. Blank means it's been set. Take a look at the differences between the parameters themselves. You can see that the parameter values did actually shift a little bit right here. Right? The numbers themselves shifted, as did the variances. They shifted a little bit. And so I'm saying this because what you're getting a sense of for this model is that not only is that whenever we make changes to the model, we might start to see other changes to each of the variables included, even if it's not a part of that section of the syntax itself. So here we saw the intercepts changed just slightly for each of these. You'll see the standard error of the second one changed slightly as well. The variance has also changed slightly. And that's an indicator that this model modification may have put us into a spot where we don't fit as well. This might be, we have to check the fit of this Model 3 right here. Model 2, if I didn't say this before, was saturated. So we know this is perfect model fit. So when we start moving to a case where model fit is less than perfect potentially, that's where we really start to see values start to change for each of these parameters that are in the model. So just comparatively, here is another scatter plot of our data with our 0 covariance. Not a whole lot that you can see different between this one and back on slide 26. That one, you see the circles are tilted a little bit more in slide 26 when we estimated the covariance, and that's because this is a correlation of about 0.14. R equals 0.14. So this is a very, very flat positive line. Whereas if we go to this one, this R equals 0, and so this is an absolutely flat line. So the difference is very subtle between the two. But in looking at these, some questions remain. Does each model fit the data well? Well, I just told you before that Model 2 is perfect fit. But what about Model 3? And by fitting the data well, that is something we call absolute model fit. How well does the model fit the data absolutely? Now I'll contrast that. So if Model 3 does not fit the data well, how can we improve model fit? What information can we get from the model on where it doesn't fit? Well, we know there's only one parameter we can add to improve the model, and that's the covariance. But I want to show you the different types of information that's out there because there are multiple ways we can typically modify a multivariate model. So that's absolute model fit. The next question would be, which model fits better? Would you rather have Model 2 or Model 3? And the reason I'm asking that is Model 2 we know perfectly fits the data. We can't beat Model 2, but can Model 3 get as good as Model 2? Because if Model 3 is as good as Model 2, Model 3 only has 4 parameters, so it's a little bit more parsimonious, which may help describe what we're trying to do. And this is the notion of relative model fit. And so when we have multiple models, we need to be concerned about relative model fit. But for every one of those models we're talking about, each one has to fit the data well, absolutely. If you only concern yourself with relative model fit, you may be comparing between two models that don't fit the data at all, and your comparison actually may be misleading because of that. So how do we answer these questions? That is the topic of the following lectures. So for now, let me wrap up by saying this is an introduction for the estimation of multivariate linear models from multivariate outcomes using Lavaan, which is a path analysis or structural equation modeling package. And in this, we saw that the model for continuous data uses the multivariate normal distribution in its likelihood function. We kind of worked through Lavaan syntax and saw what it meant for data itself. So I'm going to stop here, and we will continue on in the next lecture with our cliffhanger of how to assess model fit absolutely. Thank you for listening.